Welcome to our last chapter of Honors Chemistry. This acids and bases chapter is one of my very favorite topics. In this picture, we have a sinkhole, and it is the result of reactions between acidic groundwaters and basic rock formations like limestone. And when I said a basic rock formation, I'm meaning the chemical compound that the rock is made out of is a base versus an acid. A few days ago, I posted 2 brain trainings on Chapter 12, Kinetics. Those brain trainings are the only assessments we are doing for Chapter 12. We are not doing a quiz or a test, and they are due Tuesday, April 21st, before midnight on Google Classroom. Please email me if you have any questions on them. Today, we are learning the names of acids and bases, their nomenclature is what that means, and definitions of each. So please get out your periodic table like I have mine here and keep your common polyatomic ion list handy. We're also, throughout this whole chapter, looking at this acids and bases box, the strong bases box, and the strong acid box. So these 3 here and your common polyatomic ions are the boxes you're going to need for this unit. All right, so let's go ahead and make this larger here. First, we are going to learn the names of acids. A binary acid is an acid with 2 elements, one of which is always hydrogen. Hydrogen, if you remember, has only 1 proton and 1 electron. It typically will lose its 1 electron to form a cation with a positive 1 charge. This means it can form a compound with negatively charged anions. An acid is made of hydrogen ion and an anion. You have a binary acid when your anion is only 1 element, rather than a polyatomic anion. In this chemical reaction, this general reaction here, we have a hydrogen ion with its +1 charge, and A-, which is representing any single element anion. Excuse me. The general acid is HA. For the name of this general acid, we have a prefix in the beginning, hydro. Then you name the anion with an ending or suffix of ic. So you have to change the ending of the anion to ic. Then add on the word acid at the end. Here's your example. If our anion is chlorine, which when chlorine is an anion with a -1 charge, it's actually called chloride. So when you have hydrogen ion and chloride forming this acid, HCl, you name it hydrochloric acid. HF, with your fluoride anion, you name the acid hydrofluoric acid. Pause the video and see if you can name each of these acids. HBr is hydrobromic acid, HI is hydriodic acid, and H2S is hydrosulfuric acid. Don't confuse this last one with sulfuric acid, which we will get to in a moment. Oxyacids are acids with polyatomic anions, and of course hydrogen. For the naming convention, don't use the prefix hydro like we do for the binary acids. Begin with naming the polyatomic anion, but change the ending from ate to ic. Then finish the word acid. HNO3 comes from hydrogen and nitrate, as I'm sure you just recognized because you've been reading your list of polyatomic ions every night before you go to bed, as well as every morning as soon as you wake up. Nitrate, NO3. So nitrate is changed to nitric, and we add the word acid on the end. Therefore, HNO3 is nitric acid. Write the chemical formula and the names for the acids made with these following polyatomic anions. So go ahead and pause the video and try this. Carbonate is CO3 2-, which means it will need 2 hydrogen ions to make a neutral compound with it. H2CO3 is carbonic acid. HClO4 is perchloric acid. H2SO4 is sulfuric acid. Notice it is very different than hydrosulfuric acid that we saw on slide 4. Phosphate is PO4 3-, which means you then need 3 hydrogen ions to form a neutral compound. Therefore, H3PO4 is phosphoric acid. Now, I'm sure you're wondering, well, what about the polyatomic anions that don't end in ATE, the 8, but end in ite, ITE? Well, same thing. You're just going to change the ending from ite to us, OUS. HNO2 comes from hydrogen and nitrite, which is NO2-, the nitrite. Nitrite then becomes nitrous, then you add the word acid at the end. So HNO2 is nitrous acid. Write the chemical formula and names for the acids made with the following polyatomic anions here. Pause the video and try this. Chlorite is ClO2 with a 1- charge. Therefore, HClO2 is chlorous acid. H2SO3 is sulfurous acid, or sulfurous acid. H3PO3 is phosphorus acid. HClO then is hypochlorous acid. All right, now on to bases. Good news, bases are so much easier. A base is made with the polyatomic anion hydroxide, which is OH, and I'm going to show you where it is on our common polyatomic ion list. It's right here. OH minus hydroxide. That is what bases are made out of. I'm going to go back up to here. Therefore, bases are made with hydroxide and positively charged cations, because, of course, hydroxide is negative. You need the positives to form a compound. Remember that in compounds, the cation is always listed first, then followed by the anion. Same thing for these bases. For naming bases, start by naming the cation without changing it in any way. Don't change the ending. Then add the word hydroxide. So example, LiOH is simply lithium hydroxide. Done. That's it. Pause the video and make bases with each of these cations here. Potassium has a 1+ charge. Therefore, KOH is the base called potassium hydroxide. Calcium has a 2+ charge, which means 2 hydroxides are then needed to form a neutral compound here. So CaOH with parentheses around the hydroxide and a 2 outside, referring to just what's in the parentheses, is the base calcium hydroxide. Notice we don't say dihydroxide here. This is because the charge on calcium is always a 2+, always and forever. It can't make a different charge, which means we will always need 2 hydroxides to form a neutral compound. Same with barium, BaOH2, barium hydroxide. And NaOH is sodium hydroxide. Ammonia, NH3, is a base, even though it doesn't have hydroxide. It's the only exception that I know of, actually, which brings us to an interesting question. Since bases are more than just compounds with hydroxide, what makes a base a base? Well, to answer that, let's move on to the definitions portion of our lesson for today. Let's move that down here. All right, so this scientist named Svante Arrhenius said that an acid is a compound that produces hydrogen ions when dissolved in water. These hydrogen ions attach to water molecules to make H3O+. In this chapter, you'll see H+ and H3O+ written interchangeably. These two, they mean the same thing. Arrhenius said that a base is a compound that produces hydroxide ions when dissolved in water. For most bases, that is a great definition. But of course, our lonely little exception of ammonia, NH3, doesn't have hydroxide. So we have another definition to help us understand acids and bases. Here we have two different people, Bronsted and Lowry. They came up with a different definition. An acid donates a hydrogen ion, and a base accepts a hydrogen ion. Now, if you notice, the definition for acid that Arrhenius came up with is almost identical, whether you say that the acid produces or yields a hydrogen or donates the hydrogen means essentially the exact same thing. One thing to note here, in this chapter, we will also be referring to a hydrogen ion as a proton. A neutral hydrogen atom only has one proton and one electron, with 0 neutrons. So if it loses its one and only electron, it is now just a single proton. Therefore, we can say that an acid donates a proton, meaning the hydrogen without its electron, and bases accept a proton, the hydrogen without its electron. So don't get confused when we interchange the word hydrogen ion with a proton. Before we end this lesson, let's look at how acids and bases react together. In this example, we have an acid, HNO2, nitrous acid, reacting with water. Water, as you'll learn, is special. It can act as both an acid and a base. In this example, it's acting as the base. So the acid, according to our definition, is going to donate a hydrogen, and the base is going to accept the hydrogen ion. Important thing to note is the double arrow here. This double arrow means that some of the reactants turn into products, and then some of the products turn back into reactants. All of our previous reactions that we've seen so far are completion reactions, where every single molecule of the reactants then turn into molecules of products. This, on the other hand, is an equilibrium reaction that doesn't go to completion. When you mix nitrous acid and water together, some of the molecules will react to form our products here, but not all of them. You can think of this reaction as moving back and forth between the reactants and your products. So let's look at these products. NO2 minus is a base according to our Bronsted-Lowry definition because it can accept a hydrogen, and it would love to neutralize its negative charge because, of course, our hydrogen ion has the positive charge. So we can call it the conjugate base. H3O plus is an acid according to our definition because it can donate a hydrogen ion. In fact, it would love to do so that it could become neutral again. Therefore, we're going to call this the conjugate acid. So let's look at this with another example. Down here, we're going to look at this first. We have water reacting with ammonia. We know ammonia is a base because we know it's our only exception that is a base without hydroxide. So that's just something we know. In a sense, you need to memorize it, basically. Therefore, we know the water must be an acid in order to make this an acid-base reaction. Therefore, the water, then, as the acid, is going to donate a hydrogen ion, and ammonia, which is the base, is going to accept that hydrogen ion. Once water donates a hydrogen, it now looks like this, OH-, which is hydroxide, and it's called the conjugate base. And once the ammonia accepts that hydrogen, it looks like this, NH4+, and it's ammonium. It's our only positive polyatomic ion, and it's called our conjugate acid. Of course, it's an acid because it would love to donate that hydrogen back again, and this hydroxide is a base because it would love to accept another hydrogen and become neutral. So up here, let's look at our space-filling models. You have water, and when it loses a hydrogen, it looks like this. So water is the acid, and hydroxide is its conjugate base pair. This right here is an acid-base conjugate pair. Over here, we have ammonia with the N, the nitrogen is your blue sphere, and your hydrogen are the white spheres. When it, as a base, gains a hydrogen, it turns into NH4+, and it's the conjugate acid. So this right here is a base, and it's conjugate base pair. Let's do this example problem. Label the acid and its conjugate base pair, then label the base and its conjugate acid pair. Pause the video and try this for both of these reactions. Our acid is HCl, hydrochloric acid. We know this because acids have hydrogen and an anion. Acids lose or donate a hydrogen ion, therefore its conjugate base pair is what this compound looks like minus the hydrogen or missing the hydrogen. So here's your acid and conjugate base pair. Water must be the base in this example because it's acting opposite the acid, so it must be the base. The base is going to accept a hydrogen and look like this on the other side. Therefore, this is the base. This is your conjugate acid pair. In this example down here, ammonia is your base, water is your acid. So when ammonia as the base accepts a hydrogen, here's its conjugate acid pair, base, conjugate acid. Your acid then is water, and when it donates a hydrogen, it becomes hydroxide, and here's your conjugate base. So we have the acid and its conjugate base pair. Here's some more practice. Pause the video and write the conjugate bases of each of these following acids. Here's a hint. The conjugate base of a substance is simply the original substance minus one proton, which is the hydrogen ion. Here are the answers. Notice we only subtracted one hydrogen from each base. Here's your base. This means the charge is going to decrease by one. Here's your acid, and when it donates a hydrogen, it becomes the conjugate base here. It loses a hydrogen and a charge, a positive one charge. Therefore, it drops down to a negative from 0 to -1. H2S is going to lose a hydrogen and become HS minus. pH4 positive loses a hydrogen and a positive one charge, which drops it from 1 down to 0. HCO3 minus, since it already has a minus sign, you drop it one more down to a 2 minus sign, and it no longer has any hydrogens. Here is some more practice. Pause the video and write the conjugate acid of each of these bases. Hint, the conjugate acid of a substance is simply the original substance plus one proton or hydrogen ion. Here are the answers. Notice we only added one hydrogen to each base. This means the charge is going to increase by one for each one. Here is the last slide for this lesson. A compound is called amphiprotic if it can both donate and accept a hydrogen ion, which means it can act both as an acid or a base. These first two examples here have at least one hydrogen they could donate, yet they each also have a negative charge, so they would love to accept a hydrogen ion to neutralize their charge. All amphiprotic compounds are easy to spot in this way. Water here is the only more complicated one. It's a little bit tricky, but water, of course, is special in so many ways, and so it should come as no surprise that it can act as both an acid and a base, which we've already seen in these previous examples, which means then it can either donate a hydrogen or accept another one. All right, so that's all for now, my Lancers. Please begin working on problem set 14.1.